Welcome to the Newton tutorial series. I'm Mike Cruz with AC-Tek, and in this tutorial I'm going to be showing you how to set up belts and apron feeders and bucket elevators inside Newton. So in the previous tutorials we've talked about importing DXF and STL files and then setting up velocity and motion with them. But you can also quite easily set up to 3 belts or apron feeders or bucket elevators right inside Newton just by entering a few parameters. So on the same geometry page at the top we have our geometry radio button, which shows you all of your DXF options. And then we have belt 1, 2, and 3, and these are your 3 custom geometries, and they can be any type of belt or apron feeder or bucket elevator. So you could have a belt and an apron feeder and a bucket elevator all in one simulation, or you could have 3 belts or 3 apron feeders or whatever you like. So to set up a belt, it's quite simple. You go to any of these 3 tabs, it doesn't matter which one you use, and you specify a belt width in that very first box. And that obviously is the total width of the belt, say 1200 millimeters. And you can see what it did is it automatically created us a belt. It used a default head pulley, a default transition length, and it created a drop box for our material as well. And right below belt width we can enter our belt speed, let's say 3 meters per second. If I click show velocity vectors, you can see that we have vectors for all of these triangles, and we have rotational vectors around that head pulley. So actually, if I wanted to, I could go ahead and run a simulation right now. Nope, belt doesn't exist. Because I'm not on belt 1, am I? I must be on belt 3. That's why. Belt 3. Generate. Solver, run. Look at that. There's a belt and the material's moving at 3 meters per second. Well, what else could I do with this belt? Some of your other common options. This first section is entitled Required Belt Input, but it should actually be titled Common Belt Input, because you can specify a belt width and a belt speed and some of these other quick common parameters, and then just go ahead and set up a belt right away. So the troughing angle, by default, Newton assumes 35 degrees because it's a very common angle, but you can specify 20 or 10 or 50, or you could make it a completely flat belt by saying 0.0001. Now it's basically flat. If you want, you can even specify a 5-roll troughing angle to create a 5-roll belt. So if I said that my first troughing angle is 20 and the second troughing angle is 35, it instantly turned that belt into a 5-roll belt. So just by entering that 5-roll angle, there's a 3-roll and a 5-roll. The belt center width is that width of that center section. So for some belts, especially feeder belts, belt feeders, your center width is going to be a heck of a lot wider than these wings. So I can go ahead and say that I want this to be 650, or maybe I want it to be 850. Now this looks a little bit similar to what a belt feeder would look like. So those are the most common parameters that people will adjust when they're setting up their belts. Now we can also specify the position of the belt. So by default we create our belt at the origin with the center of the head pulley at 0, 0, 0. That's just the arbitrary position that we have appointed to denote the origin. But if you want, you can go ahead and move that belt around. If we specify an X, Y, or a Z position, you can move it 1 meter in the X and 2 meters in the Y and 3 meters in the Z. Now you can see we're offset in all 3 of those dimensions. You can also specify a belt inclination, say 10 degrees or 4 degrees or 25 degrees. And in addition to the inclination, you could rotate the belt. So if I look at a top view, this belt by default is oriented with the Y-axis, and I can quickly rotate it by 90 degrees or by 35 degrees or by 270 degrees. So using these 2 combinations, the incline and the rotation angle, I can orient this belt in any direction I want, any incline, any rotation, any orientation at all, and then I can offset it to any spot in the entire simulation. So what else can we do? We can specify diameters and dimensions for our pulleys. So if I look at a side view, by default our default pulley diameter is 500 millimeters, pretty common diameter, but I can change that to whatever I want. 600, 800, 1500, 5000. You can specify any pulley diameter. Or you can specify 0 pulley diameter. The pulley face width is the width of that face of that pulley, because commonly your pulley width is a little bit more than your belt width. So I could say that that's 1400, and we can see it's sticking out on either side. Head pulley elevation. This is the elevation of the head pulley relative to that bottom center line of the belt. So if I give an exaggerated head pulley elevation, 0.5, you can see what I mean. What that did is it basically shifted the drop box and the belt downward so that the head pulley is elevated by half a meter above this center line. And of course that's very exaggerated for this particular transition length. If we were to say 0.1, that might be a little bit more realistic. But obviously when our material is in the transition section and going over the head pulley, this little bit of pulley elevation matters. That's changing the trajectory of our material, and it's changing where it exits, where it lifts off the head pulley. So if you don't enter that, you can be slightly disturbing the results of your simulation. You got to make sure you replicate every parameter of that real belt. So we can also add a snub pulley to this if we'd like. If I enter a snub pulley diameter of say 300, it puts a snub pulley, and by default it sticks it right at that same origin location. Then I can specify a Y and a Z position for that snub pulley. Now say in Y and Z position is misleading because we can rotate and incline this belt. So what we should actually be saying is axial position and vertical position. Because if I say a Y position of -2, it pulls it 2 meters backward along the belt. But if I go ahead and rotate the belt by 45 degrees, it's still in the axial direction. And same with the Z position. That's the vertical position. If I say -0.25, now we've pulled that downward a little bit. And the snub pulley is purely for aesthetics. It doesn't really affect the simulation unless you were to happen to have material drop on it a little bit, but generally it's just there to make the simulation look more realistic. We can specify an extension length, which is how far does this extension go. I can say it goes for 3 meters, or it goes for 10 meters, or whatever I want. So instead of specifying a snub pulley diameter, maybe I want to specify a tail pulley diameter instead. Say 500. So what it does is it gives us a tail pulley, and the tail pulley is going to have the same transition and the same head pulley elevation as the head pulley did. So what happens with that tail pulley is just going to mimic what happens with the head pulley. If I switch this up to 0.2, 0.5, -0.5, it's just mimicking that. But this is particularly nice if we were simulating, say, a belt feeder with no elevation and the center width was, say, 850. That's looking a little bit more like a real belt feeder. So we can see both the head and the tail pulley, and it makes for a really nice simulation. So what else can we do? If we go to our optional input, you'll notice we created this drop box here for depositing our material. Now, if we don't want that drop box, maybe we want to use our own custom drop box that we import, or some other hopper or bin above our belt. Well, to delete the drop box, just enter 1 in this drop box section, and then it'll just completely omit the drop box. Alternatively, Maybe I want to use the drop box, but I want to split it into two sections so that I could maybe drop fine material in the front and I could drop coarse lumps in the back. So all you do is enter a value between 0 and 1, 0.5. And what that did was it just sectioned out this drop box into two sections. If I want to say 0.8, it moves it closer to the front. If I say 0.1, it moves it closer to the back. We can also specify the length and the width of this drop box. If I specify a length of 5 meters, it stretches it out in that axial belt direction. If I make it wider, let's make it 5 meters wide. So it stretched out the width, but it also increased the height so that it could maintain this same this same hopper angle. Because if we just made it wider without increasing the hopper angle, then we'd have a really shallow angle. And when you drop material, if it's especially cohesive material, it's just going to pile up in the rock box and plug up your simulation. So you want to make sure you retain that steep angle. Skirt board length, that's the length of this skirt board section right here. If I want, I could make that skirt board length 5 meters or 10 meters. So it actually increases the length of the skirt board and gives you an equal amount of belt underneath it as well. The open length is the length of our belt. The open length is the length of belt between the skirt and the transition section. So by default it's set to some percentage of the belt width. And if I wanted that to be 0, I could say 0.001. Now it's basically 0. Or alternatively, I could set it at 20. And I could have a really big open length. Oh, didn't mean to do that. Your discharge transition length, that's obviously the length of the transition from fully troughed to flat at the head pulley. So if I make this 2.5, we're stretching that out. Or make it 3 or 4. And it's obviously important to replicate the proper transition length when you're modeling your belt, because the rate at which this transitions is going to affect how quickly does the material settle outward. So if this transition happened in an instant, or if it happened in, say, 0.25 meters, well, our material is going to slop outward really quickly, and it could be giving us improper sideways velocities as we exit as it flows off the head pulley. So you want to make sure that your transition length is proper. The apron feeder and bucket elevator information, we'll talk about that in a moment. Belt speed. So if you recall from I want to say it was our second geometry tutorial, we talked about velocity control for your DXF layers. Well, these same velocity controls are available in the belt section. So with this belt, I can give this belt a start, acceleration, stop, deceleration, restart, acceleration. I can specify all those same parameters just like I did for my DXF. So obviously if I specify a start time of 10 seconds, acceleration 5, stop 20, decel 5, restart 30, and 10. What this would do is the belt is going to start up at 10 seconds and it's going to accelerate to full speed by 15 seconds. At 20 seconds, the belt would begin to decelerate, and it would decelerate over a period of 5 seconds, coming to a full stop at 25. Then the belt would restart at 30 seconds, and it would accelerate back up to full speed at 10 seconds. Over 10 seconds. So it would be back up to full speed by 40 seconds. And those are just the same inputs that we talked about over here. Head pulley cycling, we'll talk about that in just a moment. And lastly, there's the friction and cohesion and triangle size settings. So just like we can override the surface friction on our geometry layers and the liquid bridge multiplier on our geometry layers, we can do the same thing onto our belt. We can specify a belt coefficient of friction. Maybe this should be, the default should probably be higher, like 0.6 or 0.65. And we can also specify the belt liquid bridge multiplier if we want to override the value that's specified here. So our belt surface friction would be overriding this coefficient, and our multiplier, boundary multiplier, would be overriding this coefficient. That's these two values here. The skirt board coefficient of friction is the friction for this whole drop box. Certainly we want that to be really low, because as we drop material in here, we don't want the material to be sticking and clogging in this upper section. That's not the point. The whole point of this drop box is just to get the material situated on the belt so that it can enter the transfer chute or enter the simulation. Now, our max triangle size. If we were interested in analyzing the forces or the wear on this belt, we might want to mesh up these belt triangles. Another tutorial is going to talk about prepping your surfaces for analyzing the force and the wear, but for now we might just note that we might want to mesh that up, and the way we can do that with these auto-generated belts is simply specifying a triangle size. You can say, well, I want my maximum triangle size, the maximum average side length, to be 100. And clearly we're on the wrong belt. We've got to go back to belt 3. 100. There we go. So it looked at all those triangles and kept subdividing them until the average side length was no larger than 100. You could say 50 even, and that makes it even smaller. But again, it's not necessary to mesh up your belt any smaller than, say, 50 millimeters, because you're not going to increase the resolution of the wear data very significantly. Especially, you can imagine if we had say 200 millimeter spheres. Obviously these are a little lumpy, but the sphere is so big that it's going to be touching, well, the sphere itself would only be touching one triangle. But if we were using a 60 to 180 particle set, each of these lumps is so big that it's already going to be touching 4 or 5 triangles anyway. So there's no point in meshing up the triangles smaller than that. All it's going to do is increase the size of your output file and increase your computation time needlessly. So 50 is the absolute minimum. Unless, of course, you were working with a very tiny belt. If your belt width was 500 millimeters, maybe you'd want to go down to 40 or 30. But generally, 75 to 100 is sufficient. Ooh, not 10. 100. That's going to be sufficient. Okay, so let's talk about the head pulley cycle and the head pulley distance. If you recall, when we talk about our surface velocity for a belt, surface velocity for any geometry that we import, the triangles don't actually move. All we do is tell Newton that those triangles have some surface velocity. But now, when we cycle the head pulley, what we do is we're going to shuttle this head pulley and this belt back and forth in that y direction, or in the axial direction. So something you might use this for is something like a pellet feeder. I'll show you, we have an example of that. Actually, it's the same example that's on the website. But what this does is we're shuttling this whole head pulley back and forth so that we can deposit these pellets onto an apron feeder. So the point is that we have to specify a time for that cycle. Just like with our linear cyclic motion, we want to specify a cyclic time or a cycle time that represents one complete cycle, one complete forward and backward motion. So you could say that that's 10 seconds. And then you specify the distance that you want it to cycle. So if I want this to cycle by 5 meters, and now it's going to cycle by 5 meters. But it didn't create any extension here, because yet again I'm on the wrong belt. So I shouldn't have set this up in belt 3. That's just confusing. Okay, so if I go here and say head pulley cycle time 10 seconds, cycle distance 5. So what that did is it created 5 meters of triangles behind my drop box. Because in order to shuttle this out and back, I'm going to need some extra triangles I can slide underneath the drop box and slide back. Similarly, if I was to say that my cycle distance wanted to be -5, it puts the triangles out in front because it assumes that I'm going to start the head pulley fully extended, and my first motion will be backwards by 5 meters. So a positive cycle distance will shoot the pulley out, and a negative cycle distance will shoot the pulley inward first. So Now, regarding the movement of the head pulley, if you understand how the head pulley cycling works, like if we're operating a pellet feeder or if we're discharging material onto a stockpile, when the head pulley cycles back and forth, it doesn't actually move, it doesn't actually shift the entire belt. All it does is wrap that head pulley up around that belt itself. So it's kind of difficult to explain. There's a section in the manual that talks about it a little bit more. Where's my belt? Nope, must not be in that section. It must be in... 1 second. It must be, no, it must be in this section here. It must be right around here. Well, I can't find it right at this second. But there is a section in the manual, I know there is, that talks about the head pulley cycling. And the point is that if this belt has a velocity of 3 meters per second, relative to my origin, relative to my Earth frame of reference, if that belt has a velocity of 3 meters per second, then as the head pulley cycles, the velocity of that belt, the velocity of that surface will stay at 3 meters per second. Even though the triangles are moving back and forth, the total velocity is not going to be 3 meters per second plus or minus the motion of the head pulley. It's only a constant 3 meters per second because of the way that this physically works on a real conveyor. So if you don't quite understand how the head pulley cycling works, then perhaps you shouldn't be using it, because it might just indicate that you are not familiar with head pulley cycling and maybe you don't want to be simulating it until you fully understand it. But anyway, the option is there in case you want to use it, and you can read up on it on other sites. I'm sure have plenty of information about the head pulley cycling, and like I said, the manual does try to describe it pretty well. So, aside from creating a regular 3 or 5 roll belt, we can also create apron feeders or bucket elevators. And you know what I'm going to do? I'm going to go ahead and delete this belt, and we're going to switch and work in belt 1 because I don't want to work in belt 3 anymore. I keep messing myself up. So if I want to do an apron feeder, the only change from creating a belt to an apron feeder is specifying the number of plates on that feeder. So if I say this is a 1200 millimeters, let's delete my head pulley cycling. Of course, an apron feeder is not going to be 1200. An apron feeder would be more like 5000, 5 meters wide. As soon as this comes back to me, what's it doing? Oh, I see what it's doing. It's trying to mesh up my triangles really, really fine on this belt. We don't want to do that. Anyway, so belt width. Now let's just go down and specify a number of plates. Let's say we want 50 plates. Clearly not enough plates. Make it 100. Now you can see we've still got our drop box here, because even when you create an apron feeder, Newton gives you the option to use this drop box if you want to. But generally, if you're doing an apron feeder, you don't want that. You want to import your own bin or hopper geometry. So again, to get rid of that, we just set this to 1. Now you can see that the radius of this apron feeder does not seem realistic. So let's change that from 500 to 1000. Maybe even 1200. So that's looking a little bit more like an apron feeder. And just like with a normal belt, we give our apron feeder a velocity, 0.25. There's no troughing angle, there's no center width, but you can still incline this apron feeder and rotate it. So if I want, I could incline it by 10 degrees, and looking down from a top view, I could rotate it by 35 degrees. I can even take and shift the position of my apron feeder. I could shift it, 1 meter in the X and 2 in the Y and 3 in the Z. Now we've offset that apron feeder, just like with a regular belt. There's no difference. There's no face width, there's no snub pulley, tail pulley, none of that. All you specify is your head pulley diameter, and that denotes the thickness, the distance between the top and bottom plates. So there's no drop box parameters, assuming you're not using one. The open length you still can set up the length of this apron feeder by using all these parameters. So for instance, if I want to make this have 0 length, I got to set all these parameters to 0. So let's say drop box length 0.001, 0.001, skirt board 0.0001, open length 0.0001, discharge transition 0.0001. So now basically all we have is the front and the back of the apron feeder. It just looks like a pulley. But of course it's not. So we want to just modify our open length. So we want to specify the length using just that one input. So if I say 5 or 6 or 7 or 10, now I know that the width of this apron feeder is just going to be 10 plus obviously the rotation of the front and back plates. So it's going to be 10 plus 1200. Using the apron feeder, you still go ahead and set up your belt start time and acceleration, stop, decel, restart. You can do all of that same stuff. You can't set up a head pulley cycle because of course that doesn't make sense with an apron feeder. You can set up your coefficient of friction, you can set up your liquid bridge multiplier, and you can even go ahead and subdivide those triangles if you want. If I wanted 500 or if I wanted, 300. Oh, wasn't small enough to subdivide. So 200. There we go. You can make those smaller if you want to. So that's about it for setting up the apron feeder. Certainly when we talk about apron feeder motion, if you recall, with a normal belt, we talk about how the triangles on that belt, the triangles on this belt don't actually move. We just give it a surface velocity. But now when we're dealing with an apron feeder, that doesn't fly. We can't do that because as these plates circle the head pulley, they physically affect the flow. Because with a head pulley is perfectly smooth. In an ideal world, it's perfectly smooth. So we can just pretend that we are giving a velocity around the head pulley. But with an apron feeder, especially if we had fewer number of plates, where's my number of plates? Let's turn that down to 60. Let's turn it down to 50. If you can imagine, as this rotates, as this circles the head pulley, these plates physically move in such a way that affects the flow. So let me go ahead and show you what I mean there. I'm sure you probably already understand what I'm talking about, but we'll do it anyway. If I just go solver, and let's speed this apron feeder up a little bit also. Make it 0.5. And let's decrease our frame rate, or increase our frame rate. Solver, run. Now if I go to a side view, you see what's happening with these plates is, they shift in a goofy way. Well, it's a totally normal way for an apron feeder. But the point is that there's these points, these edges that would affect the material. So we have to physically move the triangles when we use an apron feeder. We don't do that for a normal belt, but with an apron feeder we move those triangles. Alright, so now lastly we can set up a bucket elevator here instead if we want to. Let's just go ahead and make a new input file and go over to our bucket elevator. Here we go. So in order to do the bucket elevator, it's a little bit different from a belt or an apron feeder. We still want to enter a belt width. However, that's not necessarily the width of the bucket. The belt width is going to be the width of the track that your bucket is attached to. So let's say 150 millimeters. Now my head pulley diameter is still the diameter of the top of that bucket elevator, the diameter of your chain, or the rotational diameter of the bucket. So we'll set that at, say, 1,000. Now if we go down here to our bucket elevator inputs, we just need to specify our pulley distance. So that's the distance between the center of the top and the center of the bottom pulley. Let's say 4 meters. So that's going to be the track that our buckets ride along. The number of buckets and the bucket geometry itself. So you can import your own custom bucket geometry. Just double click this this box right here, and it opens up a window similar to our main geometry import window. Go ahead and browse for your bucket file. And if you want, you can set an offset, or you can set your scaling factors, or a lot of the same options that you can with a regular import. So you click import, 500 triangles loaded. So then what it does is it tells you right here, it tells you 500 triangles. That just kind of, it A, lets you know how many triangles are in each bucket, and B, it lets you know that you've imported your bucket geometry and it's sitting there. So now right above that, we just need to specify the number of buckets to use. So what if we say 15 buckets? It'll automatically attach those buckets to the track, and it will also space them out evenly. So if I go from 15 to 16 to 17 to 18, it's smashing those buckets together a little bit closer. Now you'll notice with this particular bucket, it's actually beside the track. So with this particular style, the track is not directly behind the bucket. The bucket does not bolt to the track, but it bolts to the side of the track, which is just fine. What you need to understand about the bucket CAD file, when you define your bucket CAD file, the origin of that CAD file is going to coincide to where we attach the bucket to the track. So for this specific CAD file, the origin of this CAD file has to be basically right exactly here, right next to that bucket. It's outside the surface of that bucket. So if I was to redefine the CAD file and put the origin right on this back face, it would shift the bucket over and it would be right attached to that track. So with the bucket elevator, we can still give it an incline and a position and a rotation offset. So if I wanted to shift this around, I can. 1, 2, 3, and now we've offset it from that origin. I could also rotate it about the vertical axis, 10, 20, 34, 50. And I could even incline it if I wanted to. Most bucket elevators are perfectly vertical, but the option is there, even if you wanted to incline it at a 90-degree angle. Now you're working with a completely horizontal bucket elevator. However you want to do it is fine. Down here at the bottom, we use the same belt speed operations. We same belt and acceleration and decel and stop and restart. All of those options are the same, just like an apron feeder or a regular belt. You can no longer do a drop box, because certainly there's no drop box associated here. You can't do a snub pulley or a tail pulley because, again, it's a bucket elevator. You can't do head pulley cycling. So one other thing that you want to definitely be aware of, you absolutely need to be aware of this, is if you recall in one of the previous tutorials we talked about rotation, and if you are using rotation in your layer, you need to mesh up the layer, because as these buckets circle the head pulley, they're actually rotating. So the inside surface of that bucket has a much different velocity than the outside surface. And if you're only representing your bucket with a couple of triangles like we see here, you're not going to get a proper velocity gradient across both faces of the bucket. So just like with the rotation, we want to use a bucket that's meshed up properly. So I'm going to go ahead and show you. I took this same bucket geometry and modified it a bit. I made a few changes and I'll show you what those were. Well, actually first I want to make one point. Note that with this bucket, if I zoom in, you can see that this bucket has thickness. There's an inside surface and an outside surface to that bucket. But now when I open up my other bucket, my meshed bucket, boom, I did two things. I removed the outside surface, because the particles are only going to contact the inside surface. So there's no point in having a thickness on that bucket, because it's just going to be more triangles that get in the way, and more triangles that require more calculations. There's no need to have it there. And then secondly, you can see that I meshed up this bucket so that I'm going to get a much nicer velocity gradient across this face and across the bottom face of this bucket, and especially across the sides. And it's imperative that you do this. Otherwise you will not get realistic motion of the particles inside the bucket as you're circling that pulley. Because some of these bucket elevators, if you've seen a high-speed bucket elevator, the way it actually works is the centripetal force of whipping the material around the pulley helps to fling it out of the bucket. So if we don't have the proper velocities on our bucket, well, we might as well not even run the simulation because it's not going to be realistic. So you got to remember to mesh up the bucket. And currently, you cannot simply import a bucket and mesh it up in Newton, like using our equalized triangles. That doesn't apply to any of this internal geometry. So it's best if you take and mesh up the geometry externally, mesh up your bucket externally. And that also gives it the opportunity, at the same time as you're meshing it up, it allows you to remove any bucket thickness or extra surfaces or extra crap that you just don't need in the bucket. Because we want the simulation to run as fast as possible. So why don't we take a peek at an animation using this exact bucket style. This is the same animation that's on our website. So we're not going to watch the whole animation, but the point is you can see those buckets are rotating as the material gets to the top. So this isn't a very high-speed bucket elevator. It doesn't fling the material out. The material just kind of drops out and falls on the next bucket. You can tell that's very goopy, very sloppy, cohesive material, the way it all goops together. If you want, you can go to the examples section of our Newton website and you can see this exact same example. So that pretty much covers all of our different geometries in here. We talked about regular belts, we talked about apron feeders, bucket elevators, head pulley cycling. So I think with all these geometry tutorials, I think you should be ready to go ahead and set up your own geometry and set up your own belts in Newton. If you have any other questions, the manual has repeats of all the same information I've talked about in these tutorials. And if not, go ahead and send us an email at info@actek.com and we'll do our best to answer your questions. Thanks.